Well, it's my pleasure to introduce Lauren Simkins. She is an assistant professor at the University of Virginia, where she's been there since 2018. Before that, she got her bachelor's from Oklahoma State and a PhD from UC Santa Barbara, and then did a postdoc with John Anderson at Rice. And she's broadly interested in how ocean floor sediments are shaped by past glaciations and present glaciations. And also notable is Lauren's dedication to diversity and outreach. She's with some other early career superstars leading the revision of the Western Arctic ice sheet workshops. And she's dedicating a lot of her time to diversity issues as well, particularly focused on Native American and Indigenous issues. And so with that, I'd like to welcome her to talk about Beyond Reconstructions, Paleo-Perspective on Marine Ice Sheet Grouting Line Environments.
Thank you for that introduction, and thank you for having me. I just want to first acknowledge that I am coming to you from Charlottesville, Virginia, which is the traditional lands of the Monacan people who still live here and thrive here in this region, this part of Virginia. And this is a tribe that was only federally recognized as of 2018, even though they were here before the Mayflower got here, and have been living in this region for close to 10,000 years. Also, Monacans and their allies are really fighting to save Rossawek, which is the former capital of the Monacan Nation and a very important trading center for the Monacan people and other people living in this region at that time. If you are interested in sort of how tribes are dealing with infrastructure that they don't want on their lands, feel free to check out Rossawek. And so I'm going to be talking to you today about how we can use essentially geoscience to understand marine-based ice sheets. And I'm actually going to pull a fast one on you. I decided to include some information about ice flow from the paleo-subglacial bed of ice sheets and glaciers. So I'm going to be talking to you about marine-based ice sheets and thinking about subglacial and grounding line environments. And just to get us started, I think it's important to think about what is the utility in studying glaciers and ice sheets that are no longer with us, or glaciers and ice sheets that are smaller than they are, smaller today than they were in the past. And so one really critical piece of information that we can get from thinking about the past, the geologic past, is, what is the long-term context of contemporary glacial systems, right? So what's happened in the last decades, hundreds, thousands of years that sort of are leading up to the point that we are now in terms of the size and the behavior of glacial systems today. Another really important, and I don't know why that text is a different color, at least it looks that way to me. Another important piece of information that we can get is what are the possible outcomes moving into the future? So what's happened in the past? What is the full range of behavior in terms of ice flow and retreat for glacial systems? That is really important context for thinking about the future. And generally, deglaciated environments are easier to access than their contemporary counterparts, right? So ice makes it difficult to access the landscape beneath it. And in particular, if we want to think about subglacial conditions and processes, or processes and conditions at the terminus of glacial systems. So, right, it's nice. We can use these sorts of geoscience tools, I like to call them, to think about glacial systems and think about processes and conditions that are relevant for contemporary systems today in places that are easier to access. And there are a range of things that we can do when studying records of glaciers and ice sheets in the past. Right, one probably more intuitive aspect of that is just thinking about past configurations, which are critical for thinking about landscape evolution, for human migration into North America, right, which was impeded by both the Cordilleran ice sheet and the Laurentide ice sheet. It's also important for other fields of study, thinking about like terrestrial biomass, changes in vegetation through time, and then is critical for thinking about ocean conditions and how those have changed through time as well. We can also think about when events happened in the past in terms of glacial systems. And one big question is when and how quickly did glacial ice masses retreat in the past. So we can extract information about absolute and relative ages that allow us to assess variability in ice flow and retreat across time and space. And then also provide more context for in particular sea level, right? So glacial ice being a big source of sea level rise, right? So when were they contributing to sea level in the past, and how did that sea level impact landscapes globally? Oops. Okay, and we can also think about boundary conditions, and the way that I interpret boundary conditions are essentially just bed conditions. So what are the bed properties of properties of the terrain beneath ice, which I referred to as a bed, and I realize that in fields outside of glaciology, that could be a weird term. So what are the properties of the bed? What is the topography like? What is the geology like? Which are all important for thinking about how do we model glacial ice, and in particular for thinking about marine-based glacial systems sitting on a bed that's below sea level, for thinking about potential pathways of warm water that can get up close to the glacial ice or their floating ice shelves and contribute to ice mass loss. And then one of my favorite aspects of doing this type of work is extracting process-based information, right? So we can identify processes and outcomes, right? So we can say, okay, this process was taking place. Sometimes we know exactly when that happened. Sometimes we don't. And what was the outcome? So did the ice respond in a way that contributed to like large magnitude retreat events? And so we can think about ice bed interactions, subglacial hydrology. We can think about warm water incursion, getting close to the glacial ice and contributing to melting. We can also think about ice shelf collapse and what response the grounded ice sheet had to that. And then also think about sediment transport and deposition, which is important because sediment transport in the subglacial environment actually contributes to faster ice flow velocities. Okay, so this is what the glacial configuration, or similar to, or close to what the glacial configuration was like during the last glacial maximum about 20,000 years ago. Well, the time depends on where exactly you are on this map. And so what my group does is we make use of these deglaciated landscapes, right? Today we only have the Greenland ice sheet and the Antarctic ice sheet, but there were former ice sheets, and those landscapes can tell us a lot about glacial ice behavior. So try to understand these elusive or hard to get to glacial environments and processes that we know are taking place today, but we don't yet know what the outcomes will be. And so how do we do this? There are a number of methods that we can use. And so here I'm showing the methods that we use for offshore environments, so marine environments, right? So we can use geophysical data. So this is a nice sort of summary schematic showing the types of data that we can use to answer questions about glacial ice behavior. The most of the data that you will see in my talk is coming from multi-beam swath bathymetry, although you'll see some of this high frequency seismic sub-bottom profiler data. And I often find myself interested in the small landforms that are preserved on the seafloor that record what the ice did. And there's a reason why those small landforms are important. So small landforms are telling us about sort of fine scale changes in the glacial system and the ocean around these marine-based glacial systems, as well as sort of closing the gap on timescales that we traditionally think about with using geological archives, right? Maybe hundreds, thousands of years. These small landforms can form on a matter of years, decades, hundreds of years. And so sort of closing the gap between contemporary observations and then observations that we sort of traditionally think of, or timescales that we think of for geologic records. I also use offshore sediments and the water within those sediments to think about glacial change and glacial processes. But I also work in environments that were below sea level during glaciations and now are above sea level due to glacial isostatic adjustment. So in these now onshore environments, we can look at outcrops. So this is actually a really nice outcrop here of exclusively subglacial sediments, but you can see how different those sediments are. You can also see lots of different types of structures in here that tell us about processes. And this is Marion McKenzie. You can send some good vibes to her right now. She's my first PhD student who's going through her comprehensive exams right now as we speak, which is the written part. I'm not missing anything important. So she's doing her written part, which takes 2 days at UVA. We can also take cores, which are really a really nice complement to these coastal cliffs that we can look at. And we also use different types of remote sensing data, and in this case, LiDAR, to really couple what we can see with the sediments and the stratigraphy, but also thinking about landform-based evidence too. Okay, so in this talk, I will be focusing on landforms, but introducing sort of concepts that we can get from landforms, and sediments as well. So here's just a nice compilation of glacial landforms that can tell us a lot. And so in this case, I'm showing examples of glacial landforms that tell us about the thermal regime at the bottom of ice sheets on deglaciated continental margins. And here are some landforms that tell us about ice flow. And then here are a suite of landforms that tell us about ice retreat. And so you can see just, even if you are unfamiliar with glacial landforms, you can see there's a lot of variability in terms of character of these landforms. And that variability in morphology is very, very important for identifying glacial behavior and processes and conditions that are important for determining how the ice responds to those processes and conditions. So for sediments, sediments are altered and produced by glacial conditions and processes. This is a nice schematic that summarizes some of the sediment core work that we have done in the Ross Sea. So you're seeing a cross section here of a grounded ice sheet and a floating ice shelf. Based on the sediments, we can identify if there was an ice shelf or not. And we can also identify processes that were taking place right at the grounding line, which is the transition from a grounded ice sheet to a floating ice shelf, or a grounded ice sheet to an ice cliff. And so we can see, through these sediments, we can capture the processes that were taking place in this very near grounding line environment. We can also track meltwater discharge coming out from beneath the ice into the surrounding ocean. With this suite of sediment cores we were looking at in the Ross Sea in Antarctica, we could identify, we could define distances that we would expect to see meltwater plume deposits. And we could also identify a very restricted zone where we could see that the basal ice in an ice shelf was melting and dropping out any frozen material, that sediment material that was in there. So there's a lot we can do with sediments. Another aspect of looking at sediment cores is we can see who is living in these environments at the time that sediment was being deposited. And so this is just some foram work that was done by one of my colleagues, where these different units here, these are different sedimentological units, and we can see that there are clear differences in who was living there at the time. And we can also see, right, the conditions that developed when there was sort of meltwater intensive environment. So lots of meltwater being pumped into the ocean. We find that really no one likes to live there because sedimentation rates are too high. We do get very excited, right, about thinking about both geologic time. So you can see some ages here, so 15,000 years ago. But we can also look at really, really recently deposited sediments. This is showing a box core and sampling that box core. These are two PhD students, one of mine, and then one at the University of Alabama. So we do get super excited about thinking about geologic timescales, but also using sediments to think about modern processes. And these are from Thwaites Glacier, in front of Thwaites Glacier in Antarctica. So what are we going to be talking about today? So we're going to be talking about sort of a case study for thinking about ice flow, another for thinking about grounding line retreat, and then another for subglacial meltwater. And this was just the image that I showed on my title slide, where we see these are drumlins, and we can also see some subglacial channels that are recorded on the seafloor. This I wanted to include in here for any of you who work with sediment cores. Very recently, for sediment cores coming back from Thwaites Glacier, offshore of Thwaites Glacier, we got CT scans of those sediment cores, and that just revolutionized our understanding of these cores. So these sorts of laminations that you see here, these are like 1 millimeter scale laminations that, visibly we could not see. Interestingly, the composition, outside of having larger clasts in some places, the matrix composition for a lot of these cores that are just offshore of contemporary glacial systems, the matrix material is the same. So, right, we could rely on grain size if the sources of sediment are changing, but we have to also think about the structures, which are telling us more about processes. Okay, so let's think about ice flow. So there are some big knowledge gaps regarding ice flow, and especially for fast flowing regions of glacial systems. Right, these are important because they are responsible for contributing to sea level. So for the Antarctic ice sheet, about 90% of the ice that makes its way into the ocean is coming from these fast flowing ice streams. We also know that there's a lot of variability in terms of velocity and configuration of these ice streams through time and space. And we want to be able to predict, right, ice flow velocities, especially moving into the future, because that is going to reflect sea level contributions coming from glacial ice. And so there's the idea that in the absence of any changes in topography or conditions at the ice bed interface, that ice flow will sort of self-organize. And so we have sort of the center of, this is model results, and we have the center of the ice mass here. And then we have these discrete regions of warm-based ice, which would develop into those faster flowing regions of ice, those ice streams, surrounded by colder-based ice that's not really going anywhere, not going anywhere too fast. And so, in reality, that's not what we see, right? Thinking about contemporary systems, but also paleo systems as well. So this is showing the Laurentide ice sheet and time evolved ice streams. And we can really see that, that the configuration of these fast flowing regions in the purple, that it doesn't hold, right? So that leads us to think that topography or conditions of the ice bed interface are actually super important in determining regions of fast flowing ice. So one question is, does ice flow systematically correspond to these sort of catchment scale bed conditions? This is another example showing changes in the composition of the bed, so the bed geology, but you can also see that there are big changes in topography. In this case, the conclusion was that both topography and substrate geology are important in dictating where streaming ice flow can happen, those fast ice flow velocities. And so in this recently published paper that I and my colleagues put together, right, we sort of test this idea. If theory, models, and conceptual frameworks suggest that the evolution of ice sheets can be predicted based on topography and geologic setting, right, we should see similar trends across deglaciated continental margins worldwide. And so that allows us to think about how predictable glacial systems are in response to the bed conditions. And we do this through 99 different sites distributed globally across deglaciated continental margins. So all of these dots here, we're taking data sets from all of these regions to assess this question. And using the high quality bathymetric data, so high quality in this case means vertical resolutions of centimeters to decimeters, being able to resolve those really fine scale landforms on the seafloor. And in the study, we think about thermal regime, retreat, and ice flow. What I'm presenting here today is on ice flow. So we characterize ice flow into categories. So this is a category of landforms that represents ice streaming, so those fast ice flow velocities. And then we have sort of our moderate ice flow velocities, where ice is still moving relatively fast and modulated by processes at the bed, but not as fast as this case here. And so one thing that we have to do is to systematically characterize these catchment scale bed settings in all of these 99 locations, which was incredibly difficult, right? We also had to characterize ice flow in all of these locations based on landform assemblages. And after 4 years, we finally did it and got the paper published. So we characterize topography into these 4 categories here: troughs, banks, fjords, and basins. We very generally characterize substrate conditions or substrate composition into crystalline, sedimentary, unlithified sediments, beds that have a qualitatively hard to soft transition, so potentially going from crystalline beds to either a sedimentary bed or unlithified sediments, and then a category that is variable where there are more than 2 transitions in the bed. And then we also characterize bed slope. So normal would be that you have this sort of configuration, and then reverse, you have this sort of configuration where in the upstream direction, the bed deepens. And so we find that streaming ice flow is preferential in topographic settings that allow for ice to sort of be funneled. And so what we see here is our characterized flow regime, so streaming, moderate, and then indiscernible. For all of those 99 locations, this is the spread that we see. So the majority of our data set suggests that streaming ice flow was happening at the time those landforms were sculpted and deposited. And if we separate that into these different categories, we see that troughs have an overrepresentation of streaming ice flow compared to the full data set. Fjords have about the same as the full data set. And then we see less streaming in basins and on banks. Yes, we see funneling in these low confined places on the seafloor where ice could sort of be funneled into and also pile up into these low places, which contributes to faster ice flow velocities. But there is still a significant proportion of this data set that suggest ice streaming can be supported in topographic places where we do not see the potential for topographic funneling. So here's one example of a pretty subdued bank right here, where we see evidence through the occurrence of glacial lineations of qualitatively streaming ice flow velocity. And so the question is, well, why do we see evidence of streaming on these banks? Well, we think that can happen on low amplitude banks that can sort of be overrun by ice flow in places where there is topographic funneling of ice, so that fast flowing ice sort of just spills over onto these banks. And what we find is that the catchment area of the glacial systems is also pretty important. So banks that are low amplitude and glacial systems that have high ice supply to those banks, we can achieve fast ice flow velocities. And so if we're thinking about now bed slope, so here again, this is the full data set. And we can see for normal beds that streaming is underrepresented. On reverse beds, those landward dipping beds or upstream dipping beds, we actually see greater cases of ice streaming in these data sets, and then sort of the same proportion as the full data set for variable sloping beds. So interestingly, these reverse beds are encouraging faster flow velocities, but we don't see that streaming itself is contingent on any sort of bed slope. And so then for thinking about substrate composition, this is the substrate geology for the full data set. And then for looking at the substrate geology for the distribution of streaming modes, most of the cases of streaming ice flow occur on unlithified or those transitional hard soft beds. And so what's interesting, if we look at the full data set, right, this was just looking at streaming modes. If we look at the full data set and then look at the different categories here, we see that really streaming shows very little preference for any of these substrate types, which is quite interesting because we think these fast ice flow velocities are enhanced by essentially how hard, how resistant the bed is, which can create friction at the ice bed interface and slow down ice flow. But in this case, we really see that there's not a sort of predictable flow conditions on different composition beds. And so for this part, we find that there are some exceptions to these theoretical, conceptual, and model rules that banks can host ice streams, and that bed substrate and isolation is really ineffective in dictating flow style. Really, all of the results that we find for ice flow, for retreat, and for thermal regime suggest that the presence of meltwater is actually the driving factor and really critical to being able to essentially predict flow, retreat, and thermal regimes across deglaciated continental margins worldwide. Okay, so now let's think about grounding lines. We just talked about ice flow. And so here I'm showing you two different perspectives of grounding lines. This is showing contemporary grounding lines for Thwaites Glacier. Here's an ice shelf, and here's the grounded ice. And these different lines that you see are representing different times. So we can see changes in the grounding line through time here. Of course, this is viewed from the surface of the ice. Now, if we think about grounding lines, paleo grounding lines, we're looking at the basal expression of those grounding lines, right? So surface and basal expressions. What's interesting to think about is, and still an unanswered question is the basal expression of a grounding line the same as the surface expression, right? So if we want to map the sort of morphology, the shape of the grounding line, would we expect the basal expression to be the same as the surface? And the jury's still out on that. And so one thing that you might see is that these grounding lines can be quite sinuous, and in other cases be more linear. We can also see that here for the paleo record on the seafloor. And so I'm working on a project with Lee Stearns and Kaya Riverman on really figuring out why grounding lines wiggle, both using contemporary observations and paleo observations. And so if we think about variability in grounding line position through time and space, due to all of this isn't even showing all of the processes that can contribute to grounding line position and morphology, but the processes that are shown here, plus the ones that aren't, really make it hard to predict retreat moving into the future, right? But that's what we need to know. We need to know both ice flux and we need to know positions of the grounding line to be able to predict ice sheet contributions to sea level. And so one thing that we can do is we can use these ice marginal landforms that are preserved on deglaciated continental margins worldwide to understand processes and conditions that took place at former grounding line positions and allow us to identify outcomes across years to thousands of years. So how do these ice marginal landforms form? Here we're going to be talking about recessional moraines and grounding zone wedges. So recessional moraines can happen both for terrestrial-based and marine-based systems, and actually look pretty similar to each other. And they're thought to be formed by both deformational processes, so the ice sort of pushing sediments into these ridges, as well as deposition of sediment coming from the subglacial environment and being deposited at the grounding line. or terminus for the case of these terrestrial systems. Grounding zone wedges, on the other hand, are thought to be almost entirely depositional features based on the internal stratigraphy from either that sub-bottom profiler data or seismic data. And these only occur in aqueous environments and really have only been documented for marine environments. And so in places where there were marine-based systems, right, we could expect to see both paleo grounding line positions marked by recessional moraines, but also grounding zone wedges as well, which formerly were called till deltas. So you can think of them as like a delta, but instead of being fed by rivers, right, they're being fed by ice transported material and transported material at the ice bed interface. And so one question is, are there really genetic distinctions between these two types of landforms? And what can these landforms tell us about processes causing retreat? And so in this paper, we chose to answer that question with over 6,000 landforms observed on the seafloor in the Western Ross Sea, which marked paleo grounding line positions of different sectors of the East Antarctic ice sheet. And what we really find is that both landform types show evidence of deformation and deposition being important processes. So this is showing some of that sub-bottom profiler data where you can see both the bathymetry, the multi-beam bathymetry, and the cross sections of those landforms. So we see in some cases, right, that those moraines are being deposited on top of this reflector. This reflector is thought to be associated, essentially is the unconformity associated with ice advance across the seafloor, and then these moraines were deposited on top of that unconformity. So in some cases, it looks like they're purely depositional. In some cases, it looks like they're also deformational. And then if we look at examples of grounding zone wedges, we see the same thing too, where we see that these features were building up on top of that unconformity. In other places, we see that they seem to be pretty deformational, so more like push features. And so now let's think a little bit about processes. So what do they tell us about what was happening at the grounding line whenever it was parked in these different locations? So interestingly, we found that both types of these landforms these types of landforms can transition into those two end members. So in this case, we see a patch of the seafloor where there are grounding zone wedges, which are visually interpreted based on their morphology in these like asymmetrical patterns. There are other properties that allow us to distinguish these two, but that's the biggest one. We can see across a single grounding line position, right, we have some of the basal expression, landform expression of that grounding line being these grounding zone wedges, and in sort of just very quick space, that transitions into moraines. And this is reflecting processes that were taking place at the grounding line. So these both indicate that you can have significant variability in terms of sediment buildup at grounding lines. But also this represents, if you were to count the grounding zone wedges here in this space, and the moraines in this space, you would see that the retreat behavior is also different. For the same, remember, this is for the same grounding line. So the grounding line parked over here is building these grounding zone wedges, and the ice is retreating in this direction. And over here, we see the grounding line is building these smaller features, and that the ice is retreating quicker on this side than it is on this side. And so overall, this tells us that these landform products are sensitive to, we think, sediment flux at the grounding line, and then also how long the grounding line is in those particular locations. We also see that these landforms are representing two distinct styles of grounding line behavior that vary abruptly across space and time. So we really don't see any transitional features. We either see something that looks like a grounding zone wedge or something that looks like a recessional moraine. And so for the moraines, we see these small magnitude retreat events, but high frequency retreat events that seem to be driven by some cyclic or regular process that's driving retreat. And then for grounding zone wedges, we see that there are these longer duration still stands in the grounding line position, and that we think are enhanced by the buildup of sediment at the grounding line, which is affecting the minimum ice thickness that is required to keep the ice from floating and lifting off at the seafloor. But we also find that these larger generally larger grounding zone wedges are also associated with larger retreat events between features. And so this indicates that, yes, there is some stability provided by sediment buildup, but there is a threshold of stability, and then you get this large retreat event. And so now we're going to very briefly talk about some project that I'm working on, which I hope will be submitted to a journal very soon. I've been saying that for like a year now, focused on water coming out of these paleo grounding lines and into the ocean. So water flow beneath glaciers and ice sheets is really critical for understanding ice flow, sediment transport, and much more. We can characterize the styles of ice flow between being sort of, let's do over here, slow and efficient sort of distributed systems. So porous flow would be like groundwater flow, and then cavities, sort of linked cavities, and that are transient through time and space. And then also thinking about like water films, right? And then we move into these more fast, efficient, non-distributed channelized systems that are thought to drain water much more efficiently in the subglacial environment. And so we can think about these individual styles of water drainage in the subglacial environment. But in reality, there are probably lots of interactions between these different styles of retreat. And so we can see, based on contemporary observations, that there are temporal shifts in how water drains in the subglacial environment, and in this case associated with seasonal changes in meltwater production at the surface, making its way to the bottom of the ice, going from sheet flow in the early part of the melt season to efficient channelized flow. And this is linked to changes in ice velocity. And then we can also see that there are cases where there are these major spatial shifts in the style of drainage. And in this case, sort of adding subcategories into here, distributed canals versus concentrated canals. And this is beneath Waits Glacier. And this one is in Greenland. I don't know if I said that. We still don't think surface melt in Antarctica is a major contributor to changes in how water drains beneath ice. And so we really need perspectives across time and space to understand how these drainage systems, subglacial drainage systems, evolve through time, and how these styles of drainage interact with each other. Also in the Ross Sea, we have an example of what we're calling a corridor, a meltwater corridor. So this is on the deglaciated seafloor, where we see a collection of over 70 sediment-based channels, so subglacial channels incised into sediments that converge and diverge across over 60 kilometers of space. So when the ice was covering this region, it was flowing in this direction. And when it was retreating, it was doing it in this direction. And so we also see these white lines here are showing ice marginal landforms. And so cross-cutting relationships between these 70-something channels and ice marginal landforms are allowing us to, one, identify when the channels were active compared to the position of the grounding line as it retreated in this direction, but also allow us to assess the influence of channelized drainage on landform products and then on grounding line behavior. And so this is work that one of my undergraduate students is doing to think about how this meltwater corridor influenced grounding line behavior. Okay, so if we look across the 60 so kilometer length of this corridor, the topography changes greatly and variability in slope of the topography changes greatly. And so this is important for thinking about potential meltwater production associated with strain heating as ice was flowing up and over this topographic high. But is also very interesting because based on the cross-sectional area of these channels, which we are using to qualitatively think about sort of maximum drainage capacity within channels from upstream to downstream parts of this corridor, we see that there's a 3 order of magnitude change in terms of drainage capacity, which is quite remarkable, right? Because we don't think, especially at this time in the deglaciation from the last glacial maximum, we don't think that there were surface meltwater contributions to the subglacial environment. And so where did that water come from and where did it go? So these changes in drainage capacity correspond to changes in topography, but also changes in how variable slope was. And so this is really interesting to think about because that's a huge change in the potential for these channels to drain water. And so thinking about where did this water come from? Like how important could strain heating be in contributing to meltwater production in this region and other contemporary regions where ice is flowing across big bumps in the bed? And then where does that water go, right? It doesn't just evaporate into space. So what happens to that water? If you want to hear more about that, I'm giving a talk about grounding lines and water drainage next week for the global seminar series that the IGS is hosting. Okay, and I just wanted to share sort of snippets of research that my students are working on. We do a lot of things. And currently we've been finding ourselves sort of scouring data sets and working with large data sets of landforms or information coming out of sediment cores, partially forced by the pandemic, but also because we think that there is a lot of valuable information out there hanging out in data sets that people have already published on, but haven't thought about the same sorts of questions that we're thinking about. And I just want to leave and say that if anyone here is interested in potentially working with me, I am super happy to hear your ideas and help you develop a postdoctoral research fellowship application through the NSF Office of Polar Programs. There's a deadline of June 18th. So if you're looking for postdocs and sort of like these icy environments and thinking about landforms and sediments and earth surface processes and dealing with large data sets, then feel free to contact me. And then also I just want to share, because you all are coming from different fields, that there's a small group of researchers we're advocating for invisible name change policies for journal publications. People change their names for a number of reasons, and sometimes they don't want the reason to be public or even their name change to be made known publicly. So if you're interested in advocating for that, I have a template put together that you can send to different journals, different editors, editorial boards, and you can check that out on my website. And that's all I have for you.
Thanks, Lauren. So I guess we'll take questions from anybody who has a question. Do you want to just raise your hand? I knew Duncan would. I can always count on you.
Hi, Lauren. Great talk. It's, I guess on the Greenwood paper where you're doing the survey, the 99 sites, how do you take into account, or is there the possibility of preservation bias between these different kinds of landforms, especially in that last marginal phase as you're retreating the margin out of there?
Yeah, that's a great question. So preservation is key to doing these types of studies. And so we are biased towards regions that or landforms that are preserved, and regions where the ice bed interface is sort of active, There are active changes to the bed associated with these glacial systems. So we are biased. I should say that we only used positive evidence for that study. So we did not make any interpretations about the absence of these landforms that are important. So yes, we are biased, but we don't develop any interpretations based on that. The lack of landforms.
Charles?
Hi, so I came in a little bit late, but sorry if you answered this during your talk, but do you have an opinion about whether Thwaites is initiated a marine ice sheet instability? So I guess the evidence where people have pointed to is whatever the retreat that's being observed, or I guess there's been an ongoing retreat over a period of time. And I guess some of these arguments use kind of the bed form to somehow say something about the history of the retreat and whether that indicates that the train has left the station long ago and is experiencing this kind of uncontrolled retreat or unforced retreat, I guess. Do you have an opinion on it?
I do have opinions. Yes.
Yeah, okay. That's okay. Please share.
So one of the big factors sort of eating away at Thwaites Glacier now is this warm deep water that's coming from off of the continental shelf, impinging onto the continental shelf and flowing towards the ice. That warm deep water is not that warm. It is relatively warm compared to the ice. So we see evidence for Thwaites and Pine Island and other locations where this warm water was important in driving retreat in the geologic past. But we also see that there are big changes with how much of this water is coming onto the continental shelf and affecting Thwaites Glacier today. And there are factors like changes in El Nino that influence ocean circulation in this part of the world. Changes in sea ice are also important for causing circulation changes. And so we're seeing that there looks to be more of this water coming onto the continental shelf. But I should say that there is a lot of spatial variability. I think that Thwaites is not in good shape, and we should continue to expect sea level contributions coming from Thwaites moving into the future. Not that it has not been changing in the geologic past, it certainly has. But I think those processes driving retreat that we see today and we've seen in the past, today they're just exacerbated.
Patrick?
Yeah, Thanks. Hi, Laura. This was a great talk. I have a question that has actually very little to do with the results, which are very intriguing. But with the title of your talk, you say beyond reconstruction. And just from an educational perspective, which is why I belabor this point, why are you choosing this title, right? So when we teach students about the scientific process and what we do, and talk about that reconstruction is a main method, and you're saying that what you presented is beyond reconstruction. I try to understand what you mean by that.
Yeah, so basically the same data sets that we use to do these reconstructions, we can also use for other purposes. So that beyond reconstructions is, right, like taking these data sets where we have reconstructed ice extent and really thinking about processes.
But okay, so you mean reconstruction, very specifically reconstructing a specific ice extent geometry, but everything else for you is, I mean, for me, even the present day grounding line is a reconstruction, right? Because you don't actually observe the present day grounding line, you reconstruct it from your knowledge of observed ice flow.
Yeah,
and so in that sense, I mean, most of what we do is in some ways, especially in the field that we're working in, is actually a reconstruction. But anyway, I was very confused by the title, and I would still say that a lot of what's been presented would classify as a reconstruction. It's a semantic point, but I wanted to belabor this because of, again, when we talk to students about what's the scientific process, and it is, in that sense, a lot of what we do is in some ways using mental models or formal models to reconstruct sort of the knowledge. But anyway, so, okay.
Yeah, I think maybe what would make you happy is adding geologic reconstructions in there. So beyond geologic reconstructions, but I completely get your point, right? People interpret these different words in different ways, and there's no avoiding that.
Okay, great. No, okay, thanks. And I'll talk more later. Okay, thanks.
I have one question. It's probably, you've probably gotten this before, and you probably have a great answer for it. But I'm just wondering about the recessional moraines and if there could be other causes for those features than them being like terminal moraines. Could they be basal crevasse sediment fills? Could they be like calving events from big tabular bergs?
Good question. Yeah, so we do see similar sort of features, but on an even smaller scale, that are called corrugation ridges that are associated with tabular icebergs breaking off and floating seaward. But they are very limited in their extent, right? The keels of the icebergs are the ones that are impacting the seafloor. So we can distinguish these recessional moraines from those types of features. They are quite distinct, and the fact that we do see them sort of joined with grounding zone wedges does indicate that they are truly ice marginal. We do definitely see examples of crevasse squeezed ridges on the seafloor, and sometimes they can be oriented very nicely, sort of along flow or across ice flow directions. The ones that we see in Antarctica tend to be just really oddly shaped. And those ridges are really variable in terms of their amplitude across individual features as well.
Okay. All right, well, we're a little over time, so we should probably stop, but just thanks again for taking the time to come. And yeah, I think there's like an hour free still in the schedule if anybody wants to still meet with Lauren, just send me an email. Thank you.
Thanks.